Okay, so this talk is about matrix completion by using strong duality. And this is joint work with Nina Balkan, David Windroff, and Hongyang Zhang. Okay. So what is matrix completion? Oh, sorry. So basically, a classical motivating example is this like movie review. Oh, sorry. Okay. Yeah, a classical example of movie reviews. Suppose we have this big matrix where the columns corresponds to the movies and the rows corresponds to the viewers of those movies. And the entries corresponds to the scores given by the viewers to those movies. And we only know part of this matrix, basically because the viewers don't have enough time to see all the movies, or they are too lazy to write any reviews for those movies. In practice, we notice that this matrix is approximately low rank. So we can hope to use this information to recover the entire matrix. Mathematically, let's assume that this underlying exactly low rank matrix. And we get the entries that are uniformly sampled from the matrix. And we hope to exactly recover the matrix. Okay? So for simplicity, just assume that the matrix X star is a square matrix, n by n square matrix. And we can propose the following non-convex optimization problem to recover the matrix X star. Basically, we would like to find two low-rank matrices U and V, and then their product will be just low rank. And we would like the product agree with the ground truth on those observed entries. And the objective function we want to minimize is just the Frobenius norm of the product. Okay, so you can build that objective function as a regularizer. Okay. So before going to talk about how to solve this non-convex optimization problem, we would like to make this so-called incoherence assumption to just rule out some not so interesting case. In particular, suppose we only have one non-zero entry in the entire matrix. Then you need to basically sample almost all the entries to figure out the location of this non-zero entry. Okay? So we would like to basically rule out this kind of situation. Notice that in this case, it's because like most entries do not provide any information about the ground truth matrix. So we would like to assume that if we perform a skinny SVD on the ground truth matrix into A times sigma times B transpose, then we would like to assume that the rows of A and the rows of B all have small norm. Okay? So instead of having norm 1 in this bad case, we would like them to have small norm. Basically, that means that the information is somewhat like spreads out through the rows of A and B, so that it is spread out through the all the entries of this ground truth matrix. So random sampling can indeed give you some information, even with a small number of samples. Okay? So with this assumption, we would like to show how to get the optimal solution for this non-convex optimization problem. Okay, so of course, because it's non-convex, we potentially will have quite a lot of local minimum. And our approach is basically get a convex optimization problem, which turns out to be the bidual of the original non-convex optimization problem, which will share the same global optimal with the original optimization. Okay, so then we can just run any existing convex optimization algorithm, and then we just get the global optimal. Okay, so this is the idea, and the formal result is if we get enough number of sample entries from the matrix, then strong duality holds between the original non-convex optimization problem and is the dual of its dual, so which is convex. So if we have this strong duality, we can just solve this convex optimization problem and get a global optimal for the original one. Okay? So the sample complexity is basically kappa squared times the kappa is the condition number of the ground truth matrix, and times the parameter in the coherence, and times like the size of the matrix n and the rank and some logarithmic factors, which is close to the best sample complexity you can hope for. So we are going to see the best sample complexity later on. So basically, the idea is coming from this nice observation that if we observe all the entries in a matrix, then factorizing this matrix is easy. Like suppose we are given a matrix Y and we want to factorize into U and V, then we can show that all the local minimum of this optimization are just global minimum. So then you can just run, and also like the saddle points have negative curvature, and so you don't need to worry about those saddle points. You can just solve this optimization problem easily. Okay, basically this is the a very nice optimization problem. So a natural question is, can we reduce the non-convex optimization for the matrix completion to this easier form? Okay. Okay. And here's the reduction. Of course, it's we are going to see that the non-convex optimization problem is equivalent to a min-max optimization problem, where the max is over a dual variable lambda. Okay. So it's just a few lines of proof. So we begin with the original optimization problem where we introduce this h function, which is basically the indicator function measuring whether the product of u and v agree with the observed entries. If it agree, it has h has value 0. Otherwise, it just output like infinity. Okay, because it's convex and closed, we know that E equals to the biconjugate function. And then we just put in the definition of the biconjugate function. Okay, so it's basically max over the dual variable lambda and a function involving lambda. Okay, and then we just try to combine all the terms with u and v. Okay. Then we can see that under the max, we get a factorization of minus lambda and some other term related to lambda, but not related to u and v. So if we are given a fixed lambda, then it's just an easy factorization of minus lambda. Okay. So this is a nice observation because now we can just try to swap the order of min and max. Okay, so then we can get a dual problem involving the dual variable lambda. And of course, we can directly just use convex optimization to solve this problem. But it turns out that it's, if we, again, compute the dual of this dual problem, we get a much nicer form, which is much more convenient to solve using existing convex optimization algorithms. The calculation and the form of the dual by dual problem are not so important. The key thing here is that if we can show the strong duality between the min-max and max-min, then we only need to solve the final biduality problem, which is convex. Okay. So under what condition do we have this strong duality? In particular, how many samples we need for the matrix completion problem. Okay, so we can derive those conditions using like primary dual saddle point. So I've just present a little bit of the geometry intuition here. Now let's suppose that A tilde and B tilde are an optimization solution, optimal solution for the original non-convex optimization problem. Then we need to find a dual certificate lambda tilde that satisfies a bunch of conditions. Okay? And all these conditions actually have nice geometry meaning. So I'm going to explain those conditions using this figure. Okay. So the first condition basically meaning that the certificate should come from the subspace of the subgradient of H. Okay, so I draw a line there representing the subgradient subspace of the H function. And then the second condition means that the projection of minus lambda tilde on this T subspace should equal to the ground truth, where this T subspace is basically the span of the column space of A tilde and the row space of B tilde. So the ground truth is guaranteed to lie in this subspace. The only thing that condition 2 means is basically we need to have the projection of this certificate on this subspace equal to the ground truth. And third condition basically means that the component of this dual certificate outside this T subspace, orthogonal to this T subspace, should be small. Okay? So intuitively, we need that the two subspaces to have a small angle. Okay? Then it's easy to find the dual certificate. And we can show that when the number of observed entries is sufficiently large, theta should be small. In particular, when we say with high probability we observe all the entries of those of that matrix, then it turns out that the two subspaces are exactly the same, because so the subgradient subspace is just a linear space spanned by those observed entries for matrix completion. So that's why it's not difficult to show that with large enough sample, the angle is quite small, and then everything works out, and we have the strong duality. Okay. Okay. Some other questions. We can get the global optimal, but is this global solution indeed a ground truth? Okay. We need to answer this. And the second question is about what about generic matrix factorization in this form? We know nothing about H. We only know that it's convex and closed. What about this generic form? Okay. For the first question, we show that with this sample complexity, which actually match the lower bound, we can show that this ground truth matrix is the unique solution. So then basically this means that when the sample complexity, when the sample size is large enough, the global solution for this non-convex optimization is just a ground truth. Okay? Yeah. And for the generic matrix factorization, if we don't have the nice structure like the randomness in a matrix completion, we only know that H is convex and closed. Then not surprisingly, actually, it's quite hard to solve this very general form of matrix factorization, assuming the hardest of random for set. We need exponential time to get approximation solution for epsilon smaller than, say, a half or so. Okay? Okay, yeah. So this is a summary of the results. For matrix completion, we get sample complexity upper bound matching the lower bound, and we use a strong duality to get the efficient algorithm. And for generic matrix factorization, we show that it's hard, and we don't hope to get the strong duality. For future work, we would like to use this nice framework to some other problems like learning linear neural network and so on. Yeah. Okay, thanks.
Are there any questions?
We don't know whether it's the tightest or not, but it's definitely like convex whole or bounding the original one. Yeah.
Do you think that? I guess one question is, can sort of auxiliary variables, or is that not going to be the case?
Um,
I'm sort of
I
trying
mean,
to understand like how special the structure is.
yeah, so here, I think in general, it might be the case that there is some convex relaxation that are not like derived from this bidual. Because you, for example, like, if you are satisfied with some gap, you don't want you don't need a gap to be exactly zero. You are like happy with a small gap, then, right? So in that case, you can have more forms of convex relaxation, not necessarily by this bidual, but it turns out that this bidual kind of approach is a quite useful way to derive convex relaxation, in particular for matrix factorization.
So part of the result has a feel that's like a sort of sample complexity learning type result.
Mhm.
I couldn't see, is there, but I don't know, is there a way to think of it as a kind of sample complexity result, or it's a random, entry,
Um, Yeah, we derive this not particularly from that point of view, but it's possible. So basically, the sample part is embedded here from the geometry analysis point of view. Like, if you get more and more sample, then basically the subgradient subspace will get closer and closer. I'm not entirely sure whether it has a nice connection to learning.
There's another.
I was the result of
Oh,
Oh.
okay. We're back in sort of, yeah. I just have another question from the previous one. So,
Mhm.
okay, so this is for sort of exact recovery.
Mhm.
It seems like in some sense you want that so that you can actually, construct your Lagrange multiplier around the true optimum. Do you know of any ways to modify this for approximate recovery?
You can try to do that. I think the challenge, we have tried that. The challenge is that later on, when you also want to perform this kind of analysis, like with large enough sample, you kind of get close of satisfy this strong duality, at least approximately. Then we discovered that the the subgradient space is not very easy like as here. So here it's for this particular non-convex optimization, the subgradient subspace is just the linear space of the support or of the sample entries. But if you use some other like approximately matrix recovery kind of objective function, then the subgradient do not have this kind of nice form. We are still in the process of like trying to figure out how to handle that, or maybe we need like another form of analysis instead of this geometry analysis.